Okay, so series solution. So this is from chapter 7.4 in your book. So many, I've already talked about this before. We said many differential equations can't be solved explicitly, right? So we've already mentioned that many can't be solved explicitly in terms of simple functions. So you'll see that with series, you can have an explicit solution, but they won't be in the form of any simple functions that you and I are familiar with. And what I mean by simple functions are all those ones from chapter 11 where we had like the Maclaurin series, we had sine, cosine, e to the x, ln. So we're talking about those types of functions. So, so what we're going to do is use the method of power series. And we're basically looking for a solution of the form, right? Recall what a power series was. So our solution y, which is a function of x. So it was coefficients times x to the n. And this is an infinite series, right? And of course, if we expand this out, c1x plus c2x squared plus c3x cubed plus dot, 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 right? So that's our power series, general definition of a power series. And the goal of this is to figure out what the coefficients are. So this is going to be very similar to what we were doing for our second order differential equations, where we solve for the coefficients. So it should be pretty simple, easy to follow, although these problems you're going to see are pretty long-winded. A lot of algebra, and yeah, it's just some of these problems are very long-winded, so you just have to be careful. Okay, so let's look at the first example. So I haven't posted the worksheet yet on the site. I doubt that we might even get to the first problem, so I'll post it after so you guys can take a look at it. And I strongly recommend after today looking at one or two of them and try to solve it on your own so you can kind of grasp how these problems are done. So I pulled these out of the book, but we're going to use the method of power series to solve for the differential equation y double prime plus y equals 0, right? Okay, so we're going to use method of power series. So first, we're going to assume solution to be power series, which is of the form, as we mentioned above, y, which equals c naught plus c1x plus c2 squared. And you won't have to write this out every time, the expanded form, but it actually helps to see this for this first couple of steps, and you'll see why. Okay, so there's our sum notation. I'll label this as 1. Okay, step 2. Let's differentiate / manipulate our assumed solution to fit our differential equation, right? So we're just going to find if we need, obviously, if we need to differentiate. Oh, we do need to differentiate, but we may need first derivative or we may need second derivative. So obviously, we're going to do however many derivatives we need to fit our differential equation. So we're going to need y double prime. So y prime. So if we take the derivative of these terms, The first one's going to go, so this is with respect to x, dy dx. So I'll write that in here. First one will be 0 plus c1 plus 2c2 plus 3c3. You get the point. And of course, you can do this with your sum notation too. You can treat this term inside of the summation term, or the summation notation, to as a function. You can treat it as a function. So your c sub n is just the coefficient. Your x is your variable. So we're going to have the derivative to be this here, right? N minus 1. Our x is our independent variable. But notice when we go to write our index, we could start at 0, but we effectively lose this guy here. So we could write this as 1 to infinity, right? You could write 0 to infinity. But now, we should also find the second derivative. So let's find the second derivative. So this would be 0 plus, I'm missing an x here and an x squared here. Yep. Okay, so 0 from this guy plus 2c2 plus 6c3. Actually, I'm going to write this as 2 times 3 times c3. And then, of course, the next one's going to be 3 times 4 times c4 x squared. I'm missing an x here again. Okay, so now we see a pattern there. And of course, we can do this to our summation. So we'll take the derivative of this guy, which would be n times n minus 1 times cn x to the n minus 2, right? And now, since we've lost this term, we can write this as n equals 2 to infinity, right? And that was kind of the point why I wrote these middle term, this expanded form out, just to show where our indexing is coming from. Okay, so now that we have our two derivatives, so our step 3 will be to plug into our diffeq, right? As we do for all differential equations when we solve these to verify. So our differential equation was y double prime plus y equals 0. So y double prime will be this guy here. So sum n times n minus 1, c to the n, x to the n minus 2, n equals 2 to infinity, plus y, which y is this equation 1 here. So that'll just be sum of cn times xn, n equals 0 to infinity. And this whole thing is equal to 0, right? Okay, so now when we're at this step, the goal is to, there's two things we need to do. We need to match the exponent of x. Okay, generally we want to bring it down to x to the n. Okay, so I'm talking about for each of these sum terms. And so we want to manipulate it such that we have everything in terms of x to the n. And also we want to match the starting index. Okay, so there's two things we need to do. Sometimes if you do one, it'll take care of the other. Sometimes you have to do this in 2 steps. Okay, so let's look at the first thing. I always like to start with, it seems like it's easier to match the exponent of x first. So I'm going to bring the second term here. It's already in terms of x to the n, so I don't have to do anything there. The first term is x to the n minus 2. Okay, so in order to change my index such that x to the n minus 2 becomes x to the n, I need to set n equal to n plus 2, right? So if I make n equals n plus 2, so this is just for the term inside of the sum. So n becomes n plus 2. My n minus 1 becomes n plus 2 minus 1, so that's n plus 1. My c sub n becomes c sub n plus 2. And then my x to the n becomes x to the n plus 2 minus 2, so just x to the n. That was our intention, right? So now, what happened to the index is actually quite opposite of what you do. So we wouldn't add 2 to this value to make it n equals 4. Some people hastily go ahead and make that decision. But what you want to do is you want to make sure the index starts such that your first term will match whatever happened here, right? So if your n started at 2, we can look at any number of these terms. For instance, this x, if n started at 2, the first term would start at n x to the 0 power, right? So that means we need to start the index such that this starts with x to the 0. So that means n should equal 0, right? So it wouldn't be just as simple as increasing by 2 as we did the terms that are on the inside. So just be careful with that. And then the second term, we don't have to do anything. It'll just be c to the n, x to the n equals 0 to infinity. And again, as I mentioned before, by taking care of this first condition, the second condition took care of itself, right? Both of our indices are both starting at 0. So great. So, and then we'll look at an example where it doesn't and how we can manipulate that. So anyway, the next step, the next thing to note, we want to combine all of these sums to 1. Okay, so let's combine terms into one summation. Okay, so we can do that since we have the same starting index and all the terms are multiplied by this common x to the n. We can keep x to the n on the outside and then multiply or factor out the coefficient terms. So it'll be n plus 1, n plus 2, cn plus 2 plus cn, right? So I'm basically factoring out the x to the n, right? Now, from here, this is still equal to 0. And note, when we actually expand this series out, there'll be polynomials, okay? If we expand this whole series out, it'll be a giant polynomial, an infinite series, right, of polynomial terms. Well, in order for this polynomial to equal 0 for all values of x, your coefficients have to equal 0. Okay? So your coefficients here for this particular x to the n have to equal to 0. And that would satisfy that for all values of x to the n, whatever n may be, your left-hand side will equal 0. So that will guarantee that. So your coefficients have to equal 0. Coefficients for all x to the n must equal 0. So now I'm just going to extract the coefficients. Cn plus 2 plus Cn, and this will equal to 0. And I want to solve for the highest indexed coefficient C, okay? So my highest index coefficient would be Cn plus 2, which is greater than Cn, right? The index is higher. So I'm going to solve for Cn plus 2, which would be negative Cn over n plus 2 times n plus 1. Right? So this is what we call, this is called the recursion relation, which just means that if we know the first two coefficients, C1, C naught and C1, we know all coefficients through this recursion relation. And all that means is recursion just means it's a rule that defines something over and over and over. Okay, so we can express every single coefficient in terms of C naught and C1. Okay, so in order to do that, we'll set up a table. Okay, so let's set up a table, I guess, for coefficients. N here, and my recursion relation, Cn plus 2 equals negative Cn over n plus 2 times n plus 1. Okay, so what n do we start with? So you don't necessarily always have to start with 0 or 1. What dictates what n you start with is this first n should match your starting index of your sum. So what was our sum? Our final sum here. This guy here. So this one just happens to start at 0. So we are going to start at 0. So that'll be our first piece of information. But you'll see that other problems you might start at 2 or 3. So in that case, you're going to want to start with there. It's not necessarily the fact that you're going to get it wrong if you start with an earlier index. Obviously, if you start with a later index, you're missing out on some information. But if you start with an earlier index, you might find a coefficient that you don't need, or you'll find an extra piece of information. You might verify it through 2 different equations. So just know that you just need to at least start with whatever's matching your sum, the index at which it's matching your sum. So we're going to start with 0, and we'll do a few of these too. So for my example, I went up to 5. So for n equals 0, so I'm going to plug directly into my relation here. So n equals 0, this would be C2. So then if I plug this in, it'll be negative C0 over 2 times 1, right? So essentially this is negative C0 over 2 factorial, okay? If I plug in 1, we'll have C3. This will be negative C1 over 3 times 2. This will be negative C1 over 3 factorial. If I plug in 2, we'll have C4. This will be negative C2 over 4 times 3. C5 will be negative C3 over 5 times 4. I mean, you get the point. Yes, this is a bit tedious, and this is why I say these problems are pretty long-winded, because unfortunately you're going to have to do this for all of these types of problems. But as long as you follow the steps, it's not too difficult. So I know we have C2, C3, C4, and C5, but we can substitute these values because we've already found them here. We found what C2 was here. So I can substitute this guy, C naught minus C naught over 2 factorial in for C2. So I'll have minus, so it's positive C naught over 4 times 3 times 2 factorial is C naught times, or C naught divided by 4 factorial. It's the same thing, right? I can do the same thing for C5, which has this C3 term in it, and that's found here. So we can plug that in. So negative minus would be C1 over 5 times 4 times 3 factorial. So this will give us C1 over 5 factorial. And then again, we can do these for the rest of these. C4 is this guy here, C naught over 4 factorial. So this would be minus C naught 6 times 5 times 4 factorial. So C naught over 6 factorial. And then you can kind of see a pattern here now too, right? Our final results, you can kind of see that the denominator is incrementing by 1 factorial, and the numerator has this negative positive thing going, alternating from C0 to C1. So there is a clear pattern. So this next one's going to be negative C1 over 7 factorial. Okay, so here are my final results, so we can see it a little bit easier. Okay, so from this, and I find this to be the most difficult. You kind of need to see patterns here. You should notice, if you look carefully, for even coefficients, we have a pattern. And when I say even coefficients, don't look at this column, okay? And I think that could get a little bit confusing. Look at this column here. So I'm looking at the even coefficients here. Those have a certain pattern, and the odd coefficients also have a certain pattern, right? The odd ones also have a certain pattern. So the even coefficients, they're all in terms of C0, right? C sub 0. And it alternates, negative, positive. So this should be written as C to the 2n, since it's even. This should equal negative 1 to the n to alternate signs. They're all in terms of C0, and the denominator are even number increments of factorials, right? So it'll be 2n factorial, right? And then let's just plug in a few numbers here to make sure, just as a sanity check. So if we plug in 1 for this guy, it'd be C2 negative 1 to the 1 power, so negative 1, C0 over 2 factorial, and that matches this guy here. If we try 2, we get C to the C sub 4. This becomes positive C0 over 4 factorial. So it works, right? And for odd coefficients, we have everything in terms of C1 now, and also the signs alternate. So in order to make this odd, we can do 2n plus 1 minus 1 to the n to alternate, then C1 over, so now we have odd powers, or odd numbers incrementing the factorials, right? 3, 5, 7. So we'll have 2n, which makes it even, plus 1, that makes it odd. So we should have, so again, you can do your sanity check there if you wanted, but this should be good. So now we've noticed these two relationships from our coefficients. Now what we can do is plug what we found into equation 1 way above, which was our assumed solution. Right, equation 1 was this way back here, this guy here, which is essentially your assumed solution for all of these, right? It's going to be the same, because we're assuming our solution to our differential equation to be the generic form of the power series, right? Let's see. So y equals C6. So I'm just going to write out the assumed solution. Plus C2 squared plus C3x cubed C4 x to the fourth. And we get one more C5 x to the fifth. Okay. So now we've already defined what all of our even C's are going to be, right? Even coefficients. They're all going to be in terms of C0 rather. So I'll factor that out. And then I'm just essentially plugging this guy in, right? The even coefficient, that general term, but I'm incrementing by n. So if I do that, I get 1 plus, or 1 minus rather, it alternates, 1 minus 1 over 2 factorial. And then this is coming from the C2, right? So this is the C2 here. But notice we also have an x2, x squared term here. So I'm going to multiply by x squared. So the next term is going to be the C4, which if we plug 2 into this equation here, we can get our form of C4, which is positive 1 over 4 factorial. And then, of course, we need to multiply by this x to the fourth. The next term will be minus x to the sixth over 6 factorial plus dot, dot, dot. And then you can already see that there's a pattern from there. And, of course, and the pattern of the coefficients we're described here, right? And all we're doing is multiplying by the x terms that are in our assumed solution. So we're not done yet. We've only described the even powered terms. So we've only described these terms here. So that's this. So now we want to write out the odd power terms. I'll show these here. So those will be, everything will be in terms of C1, right? So the first term will be C1, which is C1. So if we plug in 0 here into this equation, we'll have 1 times C1 over 1 factorial. So it's just C1. So this is just C1, but we also have to multiply by this x, right? So the first term here will be x, and then we follow suit. We do it for all the remaining terms here. Our C2 is going to be minus x cubed over 3 factorial plus x fifth over 5 factorial minus x to the 7th over 7 factorial, so on and so forth, right? So again, just to reiterate, this is described, the coefficients of this first term is described by that, coefficients of the second term is described by that. And now we have our proposed solution. But if you recall from chapter 11, on page 768 of your book, there's a table that shows all of the common Maclaurin series. So this table gives you the Maclaurin series for 1 over 1 minus x, e to the x, sine x, cosine x, tan inverse x. And remember, we were able to manipulate these as well to come up with different functions. So if you look at this table, you'll see that sine x actually resembles this here. This is sine x. And cosine x resembles this here. Okay, what's in the bracket, rather. So this can be equated to C naught cosine x plus C1 sine of x, as defined by the Maclaurin series table, right? So Maclaurin series. So review that if you need a refresher. Again, that's on page 768. This is page 768. So this should be our solution that we found through this method. And if you notice, let's go back to the original problem, which was y double prime plus y equals 0. We didn't have to do this. This was just an example of one that we could solve other ways, just so that we can double check. So if we did this the old-fashioned way, we would take the auxiliary equation, right? So this would be r squared plus 1 equals 0. Remember, this is a second order homogeneous. And we did that through the auxiliary equation. So r squared equals -1. Therefore, r is equal to plus or minus I, right? So the solution will be of the form e to the alpha x c1 cos beta x plus c2 sine beta x. And as you can see, alpha is 0, so we're just going to be left with c1. Beta is 1, c2 sine of beta x. Of course, c1 and c2 are arbitrary constants, right? We have c0 and c1 here, but either way, they're arbitrary constants. And you can see that the solutions match, right? So any questions on this problem? I know it was a monster of a problem, but we'll have, we're going to spend the next 2 days on this as well. So any questions on any of this? I know it was a lot to digest. Okay, so let's move on. We'll set up the next problem. So this one will have slightly different complications to it. So, y double prime minus 2x y prime plus y equals 0. Let's assume solution. Right, now I'm going to skip writing out the expanded form of the power series. So we're going to need y prime and y double prime, right? So y prime will be n times c sub n x to the n minus 1, n equals 0 to infinity. Y double prime is going to give us, so this will start from 1, right? Or 0. N times n minus 1, c sub n x to the n minus 2, n equals 2 to infinity. Okay, so I'm going to change these y prime and y double prime right now to in terms of x to the n, because I know we're going to have to do that anyway. So I'll change these now. So that means for this y prime, I need to substitute n equals n plus 1, right? So that'll be n plus 1 times c to the n plus 1 x to the n. So if I did n plus 1, in order to keep it the same, this will go back to n equals 0. The second term, I need to substitute n to be n plus 2. So this will be n plus 2. N plus 2 minus 1 is n plus 1. C to the n plus 2, x to the n. And this will also make the starting index to be 0, right? To keep everything the same. So now let's plug into our diffie-q. Y double prime minus 2xy prime plus y equals 0. So this would be summation. Y double prime is here. N plus 2, n plus 1, c to the n plus 2, x to the n. Minus 2 times x times the sum of y prime, which is here, n plus 1, c to the n plus 1, x to the n, And finally, plus y, which is sum of c to the n, x to the n, right? So now, as I've said before, the two goals is to make everything in terms of x to the n, which we already did. The second is to match all of the indices. Although they're matching, we have this minus 2 to the x sitting out here. So if we put it inside the sum, what would happen? We would have minus 2 times n plus 1, c to the n plus 1, x to the n plus 1, right? So even though we had everything in terms of x to the n, now that kind of messed everything up. So we'll have to rewrite this. So the second term, we'll have to equate n to be n minus 1, right? So n equals n minus 1 at this point. So 2 times n times c to the n times x to the n equals 1 to infinity, plus sum c to the n x to the n equals 0 to infinity. Okay. So now we have everything in terms of x to the n, but because we change this guy here, it changed the index here, so that doesn't match. So we can do, really the straightforward process is to take one term out of this one and this one, but this is kind of a special case because notice this middle term here, if I just look at this one here, 2 to the n, c to the n times x to the n equals 0 to infinity. This is actually equal to n equals 1 to infinity of the same thing, right? Because we wrote out the first couple of terms. If we look at this left-hand side, if we start from n equals 0, the first term is going to be 0. The second term is going to be 2 times c1 times x to the 1 power plus 4 times c2 times x to the 2 plus dot, dot, dot. The right-hand side, if we start from 1, we're just skipping this 0, right? So these are, in fact, two equivalent expressions. So we could make this problem a lot simpler by just saying, well, that's the same thing. We can move forward. But for the sake of what to do if that wasn't the case, I'll keep this as 1 and solve it that way. And you'll see that we'll get the same result. Okay, so I'm going to just go ahead and solve it this way, as if we didn't know that these were equivalent. Okay. So that means I need to match my indices. So in order to make this 1, I evaluate this first and last sum at 0, and then change the sum to 1, starting at 1 rather. So that for this first term, I would have 2 times 1 times c2 to x to the 0 is just 1. So this would be plus sum n plus 2, n plus 1, c to n plus 2, x to the n equals 1 now. Since I took the first term out, the 0th term out, I still have this guy here. I'm not doing anything to this yet. And I'm going to take the first term out of this last summation. So x to the 0, or n at 0, is going to give us c0, x to the 0, which is just 1, plus sum of c to the n, x to the n equals 1 to infinity, and this equals 0. And now I can group all the sums inside one sum, and then I can group these two loner terms by itself, right? So I'll have 2 c2 plus c0 plus sum n plus 2 n plus 1 Cn plus 2. I'm going to factor out this x to the n out of all of them and keep it on the outside. So I'll have 2n Cn plus Cn, and then I can factor out x to the n. And these all share common starting index. So now this is still equal to 0. And remember what I said, for a polynomial to equal 0, all of the coefficients have to equal 0. And this is referring to a specific x to the n. So for this first term here, the x is x to the 0. So this is x to the 0 times all of this. The sum here is x to the n times that coefficient, okay? So those are two separate conditions that I'm going to write out. So 2 times C2 plus C0 has to equal 0. And my second condition is this coefficient, n plus 2, n plus 1, Cn plus 2, minus 2n Cn plus Cn. This has to equal 0. Okay? It's not the combination of both of these things. You have two separate equations that equal to 0. And again, that has to do with the fact that this first term is coinciding with x to the 0 power, and the second term is coinciding with x to the basically all the other x's, right? Because it's x to the n, and n cycles through 1 through infinity. So it's dealing with this. The second condition is dealing with all the other x's. So now, in order, I can solve the first equation, which I'll get. So I'm going to solve for the highest index c, which would be C2. This is equal to negative C0 over 2. And I can solve for Cn plus 2. So I'll get Cn plus 2 equals 2n Cn minus Cn over n plus 2 divided by n plus 1, which I can simplify to 2n minus 1 C the n plus 2 n plus 1. Okay, so this is my recursion relation, which we can use to set up our table to find all of our coefficients, right? So n Cn plus 2 equals my recursion relation. Here's my table. So again, I don't need to start at 0. I don't necessarily have to start at 0, and I really shouldn't, because I don't need to, because my sum starts at 1. But if I had started at 0, look what happens. C2 equals 2 times C2, no, C0 rather, 2 times C0. This should be, sorry, negative 1. Can't do algebra today. Negative 1 times C0, and then 2 times 1 in the denominator, so 2. Right, so this is equal to negative C0 over 2, and this matches exactly what we found over here. Right. So again, it's not incorrect to do it. You're just taking an extra step, and we've already found that piece of information from the first equation. So really, we could have just started from 1, which would give us C3. And this is equal to C1 over 3 times 2, and equals 2. C4 is equal to 3 times C sub 2 over 4 times 3. And I can rewrite this, since I know C2 to be negative C0 over 2, I can rewrite this as negative 3 C0, 4 times 3 times 2, which is essentially 4 factorial. And I continue to do this. I continue to do this for, I did it for 7 C's, the first 7 coefficients. So I'll just write this down. So you guys can have it. So 4 is going to be C6, which equals negative 3 times 7 times C naught over 6 factorial. 5 is going to be 5 times 9 times C1, 7 factorial. 6 is going to be C8, which is, okay, 8 factorial, and 7, which is C9, 5 times 9 times 13 times C1. Okay, so I still have a bit more left in this problem, so I'll end it here and I'll pick up next class, next discussion from this problem. But so we set up the table, and then from here we're gonna find patterns in terms of C0 and C1, and then plug that essentially back into our differential equation. So we'll finish up the problem next class. Any questions for me? Anything unclear about the process? Okay, so I'll see you guys on Wednesday.
Thank you.
All right, thanks.
Thank you.